All right, the last topic we're going to discuss in our introduction to chemical equilibria is a very powerful phenomenon that is described by a principle developed by a French scientist named LeChâtelier's. All right, and in some textbooks you'll actually see the little hat there on the A, but you don't need to put that there necessarily. But anyway, it's called LeChâtelier's principle. And this is a very interesting phenomenon that happens in chemical equilibria, and you'll see it in a lot of different places. All right, so we're going to introduce that here with a definition. And LeChâtelier's principle states when a chemical system is at equilibrium, and is disturbed, the system shifts in a direction that minimizes that disturbance. All right, so what we're going to do is look at how we are going to disturb systems, all right, and what does that mean? We're going to look at three ways in which we can disturb a system at equilibrium, all right, and we're going to see what happens when we do that. So the first disturbance we can have is going to be observing the effect of a concentration change. So we're going to go ahead and put a system under equilibrium. We're going to fill a vessel with two different gases into O4 gas and into O2 gas. All right. So we have a system, a sealed container, or vessel, if you will, that has an equilibrium mixture of these two gases. All right. So what we can imagine, like we've seen before, we just have this nice little curve, and we're sitting there at K. All right. And, you know, you're going to have this equal reaction rate going forward that you have in reverse. That is the definition of equilibrium. Now, we can come in and disturb that equilibrium by changing the concentration. All right. So what we can do is we can insert or add more NO2 gas. All right. So what we've done is we've disturbed the system. All right. And what's going to happen is the equilibrium is going to shift to minimize that disturbance. All right. So this is kind of what we've seen with Q and K earlier, but this is a little bit more of a general way of putting it. We're not actually going to be calculating to what degree it shifts. All right. So what I like to do is I like to think about stress, and when we stress a reaction out, the reaction will move away from that stress. All right. So my red arrow is indicating that we are putting in more NO2. So I'm putting an arrow down on the NO2 because we're putting more in there. All right. So we're kind of adding more NO2. So we're stressing the right side. So reaction will shift to the left to minimize stress. All right? That essentially is LeChâtelier's principle. If we stress out one side, the equilibrium is going to shift to move away from that stress. That's essentially just basically what we saw with the Q and K stuff earlier. We were at equilibrium, but then we went ahead and put in a bunch more of the product, so we artificially moved our equilibrium over here, and what's going to happen is we are going to move back towards there, so we're going to start shifting towards the left, all right? So that's kind of a graphical representation of LeChâtelier's principle, but if you can just think about stressing and de-stressing. So if we add more NO2, we're going to shift the equilibrium to the left, all right? Likewise, if I take the same reaction into O4 gas, and we have the 2 NO2 gas, if I begin de-stressing, all right, what that means is I can actually selectively pull out the NO2. So don't worry about how we can actually do that at this point, but just pretend I can magically take some cool tweezers and pull out just the NO2 gas, all right? So this is called de-stressing, all right? I'm pulling the NO2 out, all right? So what's going to happen now is if I'm lowering that concentration of the NO2, I actually have too much of this. So what's going to happen is the equilibrium is going to shift right. All right, there's too little stress on the right, if you will, so the equilibrium is going to move in that direction. All right, so it's the opposite of stressing, all right? So let's take a look at a solution reaction, all right? And you will be doing this in Lab 6, all right? So you have the simulator, and I'll be uploading a video for how to run that simulator soon, but you'll actually get to visualize LeChâtelier's principles with solution chemistry, and you'll get to see the effects of concentration and the other effects that we're going to be talking about today, all right? Let's take a container of saturated sodium chloride. All right, so what this process would look like is that we take sodium chloride solid and we dissolve it in water and we get our aqueous sodium and chloride ions. All right, so it's saturated. It cannot take any more sodium chloride at this point. So if I begin to add HCl, all right, so I'm going to add hydrochloric acid. All right, what's that going to do? Well, what that's going to do is this is going to dissociate itself to give me hydrogen ion and chloride. And if you notice, it's adding chloride. All right, so we already have that ion in here, chloride. So if I'm increasing the concentration of chloride by adding HCl, what am I doing? I'm stressing out the chloride. And I'm stressing out the right side. So that stress is going to cause the equilibrium to shift left. So what is my solution going to look like? All right. What is going to actually happen visually? What would you imagine you're going to observe? If you have saturated NaCl and you add HCl, what you're going to see, again, here's the equilibrium. By adding HCl, you're stressing the chloride, and you're going to form what? Shifting left is going to form more NaCl solid particles. Are going to start falling out of solution, all right? So that precipitation will happen by shifting that to the left. All right, we can do another trick where we could have saturated NaCl again. And instead of adding hydrochloric acid this time, I'm going to add silver nitrate, all right, AgNO3. Now, AgNO3, all nitrates are soluble in water, all right? So AgNO3 will give me the following ions in solution, all right? So notice we're not apparently going to be stressing the sodium or the chloride ion because we're making silver and nitrate ion, all right? So there shouldn't be any stressing. But if you recall, silver chloride forms a solid, all right? So when you mix silver ions and chloride ions, you get a solid, all right? So what this is essentially going to do is this is going to complex out or precipitate out free chloride with silver ion. So is this a stress or a de-stress? All right. Well, if we're pulling it out, all right, that is a de-stressing effect. All right. So which way is the equilibrium going to shift? All right. The equilibrium will shift right. So if you could monitor the concentration of sodium ions, once you saturate the solution, you can no longer dissolve any more sodium chloride, and the sodium ions would not increase in their concentration. However, if you chuck in some silver nitrate, you begin to remove the free chloride and you shift the equilibrium to the right, thus allowing more sodium ions to dissolve in that solution. So you would expect to see an increase in the amount of sodium ions in that solution. All right, so that's a trick where we can de-stress via concentration changes. All right, the next one I want to look at is the effect of a pressure or volume change on equilibrium. And this is going to have the largest effect on reactions that contain a species in the gas phase. All right, so let's go back to a gas phase reaction we've been looking at. Take N2O4 gas again, and I'm going to get 2NO2 gas. All right. So if I increase the pressure of the vessel, with an inert gas. Now, inert would be a gas that does not react with either one of these, all right? And an example of an inert gas in this case would be argon. So I can put in argon gas. What's going to happen? So just imagine I have a vessel, all right, and I start pumping in argon gas. It increases the pressure of the vessel by putting in more gas molecules that don't react with either one of these. So what is the effect going to be? Well, when you increase pressure with an inert gas, it is going to stress the side with more gas moles, all right? The side with more gas moles is going to be more sensitive to a higher pressure. All right, so we have to look at which one has more gas moles. On this side, I have 2 NO2s, and over here, I just have 1 N2O4. So what I have on the right is more gas moles. So the effect of pressure is going to affect that side more. So by stressing that side out, my equilibrium is going to shift to the left. All right, so I have more gas moles on right, thus equilibrium will shift left. So my concentration of N2O4 should go up by adding more argon gas into that container. Now, don't get confused. If I add more NO2 gas into the container, of course that equilibrium is going to shift left because I'm stressing out the NO2 side, right? That would also increase pressure, but that's not increasing pressure with an inert gas. That's the key here. We're doing this with argon, all right? We can also increase pressure by just changing the volume. And recall that pressure and volume are inversely proportional. So if I reduce the volume of the container, the pressure will go up. It's just like squeezing a balloon. All right, that pressure should go up as I reduce the volume of that balloon. All right, so if I had N2 gas and 3 moles of H2 gas in equilibrium with some ammonia gas, all right, and if I reduce volume of container, you ask, how could you do that? Well, you could have it, for example, like so, and it's a piston, and you could lower that piston, thus reducing the volume, all right, of the container. And when you would lower that piston, the volume of the container would go up, and what would happen to the pressure? All right, so the volume goes down, thus the pressure would be going up. So I like to think of these in terms of pressure, all right? So we're increasing the pressure. So which way is that going to affect the equilibrium, all right? Or which side does it stress out more? Well, we have 2 gas moles over here, and over here we have 3 and 1, so we have 4 gas moles, all right? So the left side is much more sensitive to an increase in pressure, so this is going to stress out the left side, all right? Thus the equilibrium will shift to right, okay? And the opposite would happen if I lifted that piston. If I began to lift that piston, the volume would go up and the pressure would go down, thus de-stressing the left side more, and the equilibrium would shift to the left. All right, would have that opposite effect. So I can move that piston up and down and can change the concentrations of my nitrogen, hydrogen, and ammonia. So it's a pretty cool phenomenon for sure. All right, finally, I want to look at the effect of temperature. So how would a temperature change affect equilibrium? Oh, I already wrote effect, or effect. Effect of a temperature change on equilibrium. Okay, get it right here. All right, and you have to be able to know whether, is that how you spell it? Whether, okay, whatever, we're going to go with it. Whether a reaction, I need to update my version and get a spell checker. Know whether a reaction is endo or exothermic. And if it's endothermic, heat is a reactant. And if it's exothermic, heat is a product. And this shouldn't be any surprise, because in an exothermic reaction, heat is produced, and in an endothermic reaction, heat is consumed. All right? So what we're going to do is we're going to look at a reaction here. Let's see. We'll go back to this one, because this one's actually a cool little demonstration you can look up. We can look at N2O4, which is a colorless gas. All right. And it's an endothermic process to get it to be in equilibrium, or form, I guess I should say, NO2 gas. And NO2 gas is actually kind of a reddish brown colored gas. So what you can do is you can fill a ampule, which is a fancy word for a sealed glass container or tube. So it's like a test tube, but it's sealed so the gas stays in there. You can fill it with N2O4, all right? And of course, it'll be in equilibrium and it'll form some of this reddish brown NO2 gas. However, you can shift the equilibrium from one extreme to the other by using heat transfer, all right? So if we heat up the reaction medium, or sorry, the equilibrium. So if we take that test tube or ampule and stick it in hot water, for example, what's going to happen? So let's say we heat system at equilibrium. What's going to happen here? All right. Well, there's heat right there. And if we add heat, we're going to stress out this side, just like if it were a reagent. All right. So if you can think of heat as being a reagent here, it kind of just goes back to that first principle we saw. So we're stressing out the left-hand side, so the equilibrium will shift right. So tube will get more brown. All right. So if you heat that sucker up, that ampule is going to be filled with the reddish brown gas, all right, because you're shifting the equilibrium to the right. However, you can do the opposite, all right? So the opposite erase all this, would be cooling the system. At equilibrium. So what you're doing there is you're removing heat, all right? So you can stick it in, let's say, liquid nitrogen, all right? Or an ice bath, or get it really cold, right? When you do that, that's going to remove heat, essentially de-stressing the left side. So when you de-stress the left side, the equilibrium is going to shift to the left. And what you would see is a colorless gas in ampule. It would no longer be reddish brown. It would be completely colorless. All right. So that's pretty neat, and that's something you're going to be working on in the lab, the virtual lab. You're going to have a solution of cobalt chloride. All right. And depending upon what side of the equilibrium you're on, it can be a complex that is pink or kind of a purple, or it can be a bluish color, that cobalt blue color. So you'll get to play with that. So check out the video for the lab. It's a really cool solution, and I'm glad there was a simulator for it. It's one of the prettier solutions that we work with in teaching labs. All right, so that'll do it for LeChâtelier's principle. And in fact, that will do it for our introduction chapter on chemical equilibria. All right. So we'll be going into acid-base chemistry next, but that won't be until exam 3. So this ends the material for exam 2. All right. And that will be posted tomorrow morning. All right. Thank you very much.